Hello, welcome to the OSC Colloquium. My name is Saikat Guha. My pleasure to introduce today's speaker, Dr. Hari Krovi. Hari is a senior scientist with Raytheon BBN Technologies, the Quantum Information Processing Group, based in Cambridge, Massachusetts. Hari is a long-term collaborator and a friend of mine. We have collaborated on many projects in quantum information science during his time at BBN. He came to BBN in 2012 after doing 2 postdocs in NEC labs and in University of Connecticut. And before that, he did his PhD at University of Southern California with Todd Brun, a quantum information theorist. And Hari's specialty is in quantum algorithms and complexity, but he has also worked on a wide variety of problems in optical quantum networks, quantum repeater designs, QKD security proofs, and various topics in optics-based quantum information processing, and he brings to bear his expertise in quantum algorithms and complexity to these problems. Looking forward to his talk on a high-dimensional quantum Schur transform.
Thank you, Saikat. I guess this is on. Okay. So, I put an introduction on quantum mechanics, groups and representations, and Schur-Weyl duality, and then before I get to my algorithm on the Schur transform. But feel free to stop me at any point and ask questions. And if something's not clear, I can even try to draw something out on the board or on the paper. I haven't put in many equations or anything, and there are no proofs. But hopefully, I can give you an intuitive. Oh, sorry, I have to keep doing this. Hopefully, I can give you an intuitive picture of why this Schur transform is important and why it works, and also why Schur-Weyl duality. In fact, that's the main thing that I'll try to explain to you. Why this is a very interesting and important thing. Okay, so first is this disclaimer, which Saikat knows very well, which I have to put, but I won't read through it. It doesn't, you can read it, and we'll just switch to the next one. Okay, so this is how the talk is structured. As I said, first I'll explain to you very briefly introduction to quantum computing. You must have obviously heard of it, but then I'll just give you a little bit of a flavor for circuit-based quantum computing. And then groups and representations, but this will be quick. But again, intuitively, hopefully, you'll see what groups are and what their representations are. But we'll switch to representations of 2 specific groups, because they're the ones that appear in Schur-Weyl duality. It's the symmetric group and the unitary group, and I'll explain what they are and what these representations are. And then a very important topic called subgroup adapted bases. This is essentially what makes a transform, designing a transform, kind of difficult, but also important. We have to get to these, or this particular basis in the representations. And they're important because they have many applications, and they're kind of nicely structured, and I'll explain why. And then we'll see, this is all in the abstract, and then we'll see Schur-Weyl duality, which is the duality between these 2 groups, and I'll explain what that means. And finally, we'll come to the quantum circuit for the Schur transform. Yeah, as I said, please stop me at any point. Okay, quantum computing. So quantum computing, you may have heard, is essentially the quantum version of classical computing. So instead of computing with bits, which are 0 or 1, you're computing with qubits, which can be in any superposition of 0 and 1. And in fact, if you have 2 qubits in some superposition 0 and 1, another one in some other superposition, you can perform operations on these 2, which you cannot write as a product state, which is no longer product state. And such states are called entangled. And entangled states are extremely important. In fact, one can say that they are the reason why quantum computing works, as in it's more powerful than classical computing. So Richard Feynman is usually credited with the first ideas, although I think Manin and some others were also discussing it at the same time. But he essentially said, if you want to simulate quantum systems, which people were trying to do back then, what you need is not try to cram more and more of those into classical computers. If you build a quantum computer, then simulating quantum systems becomes somewhat natural, and easier. Of course, he didn't discuss the complexity and what algorithms one can implement and things like that. But he had a very strong intuition that if you build a quantum computer, a computer is made out of quantum systems, then they can be mapped on, or physical systems can be mapped onto them very easily, and you can simulate them. So essentially his quote, which is, well, I've seen people quote this part of it, and this is from this journal he's published in. He says, nature isn't classical, damn it, but if you want to make a simulation of nature, you'd better make it quantum mechanical. Actually, there's more. I mean, this is from the paper. And he says, by golly, it's a wonderful problem because it doesn't look so easy. And you know, those of us who work in this area know that very well, right? It's not easy at all. But on, you know, building it has many challenges. And in fact, you know, we're now at a stage where many companies and I haven't listed the startups. Actually, startups will probably take 15 or 20 slides. But many big companies are looking at quantum computing. And all the companies I've listed here are essentially looking at what's called full stack quantum computing, meaning they're building not just a small part of a quantum computer which can be used in a system designed by others, or like a software part or something like that, but they're essentially going from, you know, building the chips to the software to the input, output, and all kinds of things. Okay, so each one, it looks like, is tackling one of the big models of quantum computing. Okay, so the quantum computing can be thought of as you know, having many different models. So before I explain the models, what's the model for classical computers, like, you know, our laptop? Well, data is encoded into bits, you know, zeros and ones, and you apply gates, right? The NAND gates and whatever, you know, they apply. In fact, the NAND gate's enough in the classical computing. So it turns out that a model like that is essentially what's called circuit-based quantum computing, and it's the most popular one because many algorithms that people have designed on paper for various problems that work much faster than classical computers, than on classical computers, are in this model. So building an actual computer in this model is extremely important because you can apply those algorithms, right? And this model is implemented in IBM, Google, Rigetti, and BBN, where we're working with IBM, actually. And they're all working with superconducting qubits, and they implement the circuit-based quantum computing, and they can implement any of these algorithms. Then there's adiabatic quantum computing, and in a sense, this is the first quantum computer. And essentially, only two companies are working on this, Google and D-Wave. Google has only recently started working on that, and D-Wave is the company that's been doing this. They got into it very early, and at that time, qubits didn't have good coherence times, and they kind of just tried to scale it up instead of designing a better qubit. And so the model itself is okay, but their machines have, well, many issues in the sense that there is no demonstrated speed up on any problem so far. But the model which they base their machine on is actually equivalent to the circuit-based quantum computers. So in principle, you can, you know, take an algorithm from one and map it onto the other. Then there's the topological model, which is actually also circuit-based, except that it uses physical systems that have inherent topological, you know, properties. It's somewhat measurement-based as well, because the model of, you know, the topological properties, or the anyons they're called, that they pick, are not universal, as in you can't do all of quantum gates with those anyons. But you can if you measure them in the middle and feed forward those measurements. So it's not cluster-based, like in the optics case. It is still circuit-based, except that you have to do intermediate measurements. So it's measurement-based in that sense, measurement-based circuit model. But the big advantage of using these topological properties of these physical systems is that it offers inherent error correction. If they get this to work, they're actually the farthest behind. They don't even have a single qubit, okay? And they haven't braided, they have to braid them to implement a gate. But when they do, they will beat everyone else simply because they don't have to do error correction. Error correction is the biggest, right now, the biggest kind of the bottleneck. So right now, all these companies are putting out chips which are not error corrected. So, you know, they have 15, 20, and very soon close to 100 qubits, which will be online, and people can go and, you know, do, you know, like run algorithms and stuff. But they all have a lot of errors. And if Microsoft manages to get qubits out, they are error-corrected qubits. So to run like for example, to factor a 2,000-bit number. I mean, as you probably know, factoring is easy on quantum computers. So to factor 2000-bit number using fault-tolerant quantum computing, it takes 10 to the 6 physical qubits. That's crazy. I mean, right now we're not even at 20, 20 or 30. 10 to the 6 physical qubits. When these guys, finish their, braiding and stuff like that, 2000 bits will require just 2000 or twice that number anyons. So it's a big risk, big payoff kind of thing. And when they're the only ones who are working on this, then cluster model is also called sometimes measurement-based, is essentially very popular among the optics-based implementations. PsiQuantum and Xanadu are working on this. I guess Xanadu is also thinking of CV-based clusters, right? And finally, there's quantum walk-based computing. I won't say anything about this, except that no one's looking at this because it hasn't been developed very well. But it's another model that's also universal, meaning you can do all kinds of computing with it. Okay, so I'll go slow on the introduction, but then when we get to other stuff, I'll try to speed up a little bit, just to focus on the intuition. But stop me at any point. So this is all circuit-based quantum computing. As I said, you encode into qubits, and then you apply a sequence of gates, and then you measure. Okay. So measurement is not something anyone talks about classically, because measuring is, just looking at whether the bit is 0 or 1. And after you've looked at whether it's 0 or 1, it still is 0 or 1, unless someone goes and changes it, right? Whereas in quantum, that's not the case. A qubit can be in a superposition of 0 and 1, and when you measure it, it collapses. The state gets collapsed into 0 or 1, and from then on, it's that state until you go and change it. So each time you measure a superposition, you might get a 0 or 1, at different times, depending on with some probability, right? So measurement is something very important in quantum computing, and in fact, very often that gives you some of the power of quantum computers. Okay, so there are many types of quantum gates. You'll see C-naughts, Hadamards, Toffelees, phase gates, T gates, X, Y, and Z rotations. You don't need all of these. You only need some of these to make it universal, but having a bigger gate set is good. But then if you're trying to do a fault-tolerant way of doing, implementing quantum computers, then it's not easy to make all of these fault-tolerant. So you try to minimize your gate set in that case, and C-naught Hadamard phase plus T is enough. So people who are looking at fault-tolerant-based circuit quantum computing can make C-naught Hadamard phase fault-tolerant. T gates are the problem. So they try to minimize the number of T gates in their algorithms. So different models have different bottlenecks, and so the optimizations are different. So, quantum computing can be thought of as a quantum version of reversible computing. So in a sense, reversible classical computing became important because, our computers dissipate heat because we don't care about making sure that the computer's state goes back to its 0 state. It started out 0 state, and we don't care, we try to do things in such a way that you cannot go back to its original state, meaning that we lose information. And it's been shown by Landauer, many years ago, that if you do that, then you cannot help but, the machine will dissipate heat. And this is one of the big problems in computing right now, which is the heat, heat dissipation for big superclusters, for example. There's one reason why a lot of these are above the Arctic Circle, right? Because they find huge area over there and have this giant, server farm in there, because you don't have to spend as much energy trying to, release the heat. But quantum computing, in principle at least, can be completely reversible, except when we do the measurement. The measurement have to be destructive. But unfortunately, in reality, that's not the case. Although you apply unitary transform, the amount of input-output, the I/O stuff that you need, is actually the amount of power that it takes is quite high. But in principle, if we can figure out ways around it, you can actually implement almost completely reversible computing. Yeah.
What do you mean by destructive measurements?
Oh yeah, sorry, I didn't have. So usually a quantum state is fragile, right? So you have in fact, a photon is a good example. So a photon can be encoded in 2 modes, and that's a qubit, and you can apply gates on them like beam splitters and other things. And when you measure, you detect the photon. in principle, if you have a non-demolition measurement, after you detect the photon is still in the mode, one of the modes, and it projects itself into one of the two modes, and could still be there, and you can use it again. But most measurements that we can implement right now are not that kind, right? So the photon gets lost, and so you have to bring in a new photon. So the whole thing would not be not be reversible because of this. And there's similar problems in other implementations as well, where the qubit is now gone, and you have to put it away and then prepare a new one. Okay, so yeah, so this is the connection to reversible computing, and essentially in quantum, instead of a reversible stochastic matrix, what you have is a unitary matrix, and all of quantum computing essentially can implement unitary matrices, and arbitrary unitary matrices cannot be as easily implemented as a short sequence, but you can break it down into sequence of gates. So this sequence of gates, what I mean by they are universal is that any unitary transformation can be written as the sequence of gates up to some small error. So you just write it as a long sequence. The sequence could be very, very long, but in the end, it'll get very, very close to that arbitrary unitary transformation. So you can get as close as you want, in fact. So if you wanted to, you fix an epsilon and you say I want this close, a sequence to be this close to the unitary, then you can design a sequence that's something like log 1 over epsilon cubed, I think, long, that will get you there. Okay. Okay. So the last thing I want to say here is that just like in classical computing, you have scratch bits. So you can take some bits that are in initial 0 state or something as something that's useful to do a computation, and we call them ancillas in quantum computing. So you have a set of qubits you want to do computation on, but it's useful to take another set of qubits and all in 0 state, and then you apply some gates and then do some computation, but then you have to return these original, the scratch bits back to a 0 state. That's called uncomputation. So in quantum computing, you have to uncompute those scratch bits all the time. You can't leave them entangled because your results will be kind of lost in that entanglement, and you have to extract them, right? So if you want to compute a function f of x, where x is some bit string, then it might be easier to calculate some other function p of x and compose the two to calculate your f of x. And p of x could be a partial result. This could be in the scratch bits, but then you have to uncompute it at some point. So this is always one problem where, in fact, it's a stumbling kind of block where people think that they've computed something which is inside some kind of set of superpositions, but then don't realize that you can't just extract an amplitude of a quantum state. And in fact, its complexity of extracting an amplitude is quite high. It's sharply hard, so we can't do that. All you can do is measure and approximate that amplitude. Okay. So here's some examples of quantum circuits. This is a very famous quantum circuit called phase estimation. It's a subroutine, in fact. So phase estimation is designed by Kitaev as his own way of doing Schur's factoring algorithm. So someone told him that Schur has come up with an algorithm to factor integers, and he went and tried to figure it out himself. And his way involved phase estimation, which turns out to be, you can pull that out of his algorithm and use it as a subroutine, and it turns out to be an extremely useful subroutine, which is used in not only exponential speedups, but also polynomial speedups. Pretty much every algorithm, like HHL, if you've heard of that algorithm, which solves linear systems of equations, which has been used in machine learning and other things, essentially uses phase estimation. I won't explain this because although I kind of use it, when I get there, I'll explain a little bit. But the idea of developing an algorithm now is essentially use some of these primitives and see what happens when you apply these primitives to your problem, right? Here's another example of a quantum circuit where you want to do something called a Toffoli gate, where it's on 3 bits. It's actually a classical gate. You can think of it as a classical gate. So if this bit and this bit are both 1, then this is flipped. And if this and this are both zeros, or even one of them is 0, then nothing happens to this. Okay? So that's what this gate does. And that, if you want to break it up into your Hadamard, T, C naughts, and phase gates, then this is the whole big circuit for it. And this is one of the problems, and this is essentially called compiling, where you want to apply a more complicated gate or even a more complicated unitary, and you have to break it up into a sequence of gates. And you want to build enough of these primitives in your quantum programming language that you don't have to do this every time. Okay, so these are some examples of quantum gates. Okay, so if there are any questions, let me know. If not, we'll switch gears to the next part on groups and representations. Okay, questions? Oh. So groups and representations are kind of important in this talk because, as I was saying, what this algorithm does is essentially come up with a nice basis for the action of two different kinds of groups, the symmetric group and the unitary group. Yeah?
So you mentioned the set of tensor, you mentioned the cluster state. The pictures of the phase estimation gate and the Toffoli gate, is that convertible to an optical circuit in an obvious way, or could you
that's a good
talk about
question.
it?
So when you say optical circuit, you mean in the cluster model, or? Okay, so here's a simple way to convert into an optical circuit. Use Chuang-Yamamoto conversion, which uses a pi strength Kerr nonlinearity, but that way of doing it essentially converts a C0, which is essentially a beam splitter on a dual rail qubit, and you have your phase gates and you have your this Kerr nonlinearity is a oh, I'm sorry, that's a C0, right? That's a control phase. I'm sorry, control Z. A beam splitter is essentially a Hadamard. That's right. So anyway, so you can map each of these into optical elements, and then you can run that circuit. But we don't have access to that strong Kerrs, right? So there are the schemes which use either weak Kerrs or maybe just no Kerrs at all, and like the clusters. I'm sorry, the KLM scheme. So using the KLM scheme, you can actually just convert this easily, right? Because wherever you need a deterministic C0, you use the KLM scheme essentially, which uses many ancillas to prepare that for you. So it's easy to convert in that sense. But converting it to a cluster-based approach requires a little more care because it's a slightly different model, right? It still encodes into qubits, but then, yeah, you have to go through that map that shows that the two of them are equivalent to do that. And this is the problem, that the more kind of esoteric the model is, and even though there's a map between the two, I would say adiabatic. How would you convert Shor's algorithm to adiabatic? It's far from obvious. In fact, people are trying to figure that out even now. So you could say, well, someone showed the two are equivalent, so someone obviously mapped out one to the other. So why don't you just follow that map? It'll just be a very cumbersome map. Like, you can just go through it, and even just writing it down will be very, very difficult. Ideally, you'd like something simpler, and maybe there's something simpler that actually exists, right? So finding out an algorithm that's been designed in one model, what it looks like in another model is not that easy. Yeah. In the optics case, I think it's easier because measurement-based computing is much closer to circuit-based computing than other models. Okay. So yeah, groups. So if you haven't heard of groups, they're very, very important in physics because they kind of are a way to make symmetries of systems precise. So physics is all about symmetry, in fact, right? I mean, most physical systems have a tremendous amount of symmetry, and to talk about the symmetry and to make use of it, to say something useful about your system, you have to use the language of groups and representations. So groups are essentially nothing but it's just a set with an operation. Okay, so this is a discrete group, but we'll go to continuous groups in a minute. So you have G1, G2, G3, and so on, and there's an operation called multiplication. So you can only multiply. There's no addition or anything else. Okay, and it has to satisfy a set of axioms, meaning that if you multiply two things in a group, the result has to lie in a group, in the group. Okay, that's called closure because your operation has to be closed. And associativity is simply saying that if you multiply two things and then multiply it by the third one, that's the same as multiplying the second and third and then multiplying the first. You must have seen these things before. The existence of identity and inverse are important here. Identity just says that there is something like 1, which you can multiply to any number and doesn't change the number, right? Something like that. So it says E is the identity, which multiplied to A will just give you A. And inverse essentially is something like 1 over some number, right? Essentially, what this is saying is that there is an inverse for every element such that you multiply it by that inverse and give you the identity. So 1 over some number is like the inverse, right? It gives you a 1. And you'll see that numbers are nice to think about, especially numbers mod something as examples. But then you'll see that there are more complicated groups. In fact, we'll see the symmetric and unitary groups in a minute. So a simpler group than the symmetric group is probably the dihedral group. It has 2n elements, and the cyclic group that I mentioned. Cyclic group is simply just saying that you do modulo 3 addition, right? You have 0, 1, and 2, and you can 0 plus 1 equals 2, and 2 plus 1 equals 0, and so on. Like you can just do additions in that, and you can take any number of elements like that and do modulo n, modulo p, whatever. And the dihedral group essentially takes that cyclic group and tacks on an additional rotation symmetry, and you'll get a non-abelian group. The cyclic group is an abelian group because it's commutative, as in A times B is the same as B times A. But in most groups called non-abelian groups, that's not the case. And non-abelianity, in fact, has a direct impact on representation theory, and we'll get to that in a second. But dihedral group, even though it sounds very simple, is actually very useful in understanding the chemistry of molecules. So it turns out that when people were trying to look at, in fact, this was true in spectroscopy of crystals. I don't know much about this, but I know groups were like first, kind of used in that in a spectacular way, in a sense, right? Because people were trying to understand why certain frequencies appear when you do spectroscopy versus some don't appear. And that has to do with the symmetry of the crystal. People had a vague idea that symmetry has something to do with it, but when mathematicians started looking at this, they explained how the group representation theory explains exactly where the frequencies appear, which frequencies appear and which don't. And this was like a big surprise to people working in crystallography. And since then, in fact, it's been applied to like many other things, chemistry and stuff like that. And now fundamental physics, it's actually all about continuous groups and their representations. Here's another example. Yeah.
The cyclic group is 0 to some n-1.
n-1, yeah.
Addition modulo n.
Yeah.
That's the cyclic group. So what do you do to that? Go to the dihedral group?
Oh, you append another element called the rotation. So here's the example. So cyclic group here, it corresponds to rotating it little by little. Okay, the cyclic group has a generator, like 1, right? So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, and 1 can generate the whole group, okay? So that adding by 1, addition by 1, it corresponds to rotating it by this primitive angle over here. So you can rotate it once like this and another time, and as you keep rotating it fully, it comes back to the original point. That's like getting back to 0, okay? But this has another set of symmetries, which is flipping it over this plane, okay? And that is the additional element in this. When that element multiplies to every element of the cyclic group, that gives you the 2n elements. So you have, in fact, you can call it, S and R. So S squared, S cubed, and so on, all the way till S to the n-1 is the cyclic group. And R is this a flip, which is its own square. So R squared is identity. And RS squared, RS cubed, and so on will give you the rest of the elements. So it's kind of simple in the sense that it's like a simple extension of the cyclic group, right? So, but actually in quantum computing, this gives rise to a very hard problem. But I won't get into that right now. Sorry? Yeah, it is. And that's what we'll talk about. In fact, the symmetric group, which is what I was calling it, and the permutation group is one and the same. The symmetric group is essentially the set of permutations of n elements. It's called symmetric group, permutation group, and all kinds of things. So the symmetric group is not this group of symmetries of the Rubik's cube, but then it's a subgroup of that. And also other molecules have rotational symmetry and things like that. So symmetric group appears in things like this in nature, but it appears in many aspects of mathematics. I mean, very often you have structures where you can permute things, meaning that you can interchange 1 and 2 and 2 and 3 and so on, and there's all the symmetry which you want to use. And very often you can think of symmetry as redundancy in your description of the problem. Because if you have a problem description where if you interchange two parameters, for example, and nothing about the problem changes, then it's like you haven't really boiled that problem down to its bare parameters, so to speak, right? This symmetry can be gotten rid of by looking at representation theory and looking at one of the representations where you've already taken into account this symmetry. So you don't have to worry about every time you get a solution whether the flip of that solution or the interchanged version also gives you a solution or not, right? So if you have n elements and all possible permutations are allowed, then you have n factorial, possible permutations, right? And that's the size of a symmetric group of order n. Okay, so you have n elements that you can permute. So in our case, we'll see what those n elements are. They happen to be vector spaces, which are tensored, and we can permute these vector spaces. Okay. Okay. So what are continuous groups? Continuous groups are essentially continuous versions of the discrete groups that we've been looking at. Discrete groups are where you have discrete points which you can add or multiply, and you get a group structure. Continuous groups are where you have like an infinite number of points, and you can multiply the points and get other points. So such groups have been first investigated by Sophus Lie, and that's why they're called Lie groups. And they have group structure in addition to topological structure. Okay, and in fact they have differentiable structure as well, because they have they are differentiable manifolds. So if you heard the word manifold, that's essentially what they are. Manifold is essentially nothing but a differentiable manifold. Is nothing but a complicated looking shape where you can take a small enough patch of that shape and map it to some high dimensional real number system, meaning you can map that to R to the n. Okay, R to the n is essentially real vector spaces, right? So we understand those very well. So if you can map a complicated looking shape patch by patch to this real number system in such a way that the maps that you're taking, patch by patch, are differentiable maps that you can differentiate and use all the things that we know in real vector spaces, and using these maps you can map it back to the manifold. And of course all those calculations can only be done patch by patch, but if you can stitch those patches together, you can say things about the manifold. That's essentially what a differentiable manifold is. A Lie group is where you have that structure and group structure. So this gives a very rich structure to this manifold, which you can, which allows you to say quite a few things about these groups. It turns out that every manifold has something called tangent space attached to it. Tangent space is nothing but, for a manifold, it's a set of directions in which you can go from that point. Okay, on a flat plane, from any point you can go exactly in all the directions, that are equivalent to the plane. On a manifold, the set of directions keeps changing as the shape of the manifold changes, but it has the same dimension as the manifold, and that's called a tangent space. For a Lie group, it turns out that the tangent space at the identity element is called the Lie algebra of the group. I won't get into the details here, but Lie algebras are essentially they kind of they capture everything about the group in a sense. So understanding Lie algebras helps you understand the group itself. And in fact, this is how Lie algebras were completely classified in the 19th century, by understanding Lie algebras and their root systems and all the math that goes along with it. So so most of the time when people deal with Lie groups, at least in physics, they actually deal with the Lie algebra. And that's enough because that has all the structure in it. And Lie algebras, it turns out, are just vector spaces. So it's very easy to deal with them. But they have special properties. They have something called the Jacobi identity, which allows you to do commutations. Okay, Lie groups play a very important role in physics, especially quantum physics and quantum field theory. In fact, if you've heard of the Standard Model, right, which is our current understanding of all the particles that we've observed so far, that is essentially grounded in Lie groups. In fact, there's a certain group which is the basis of the Standard Model. Okay, and you can kind of explain everything in all the particles and everything as irreducible representations of these groups. So Lie groups started to play a very important role there, and essentially took over all of fundamental physics, quantum field theory. But there's other applications as well. The symplectic group plays a very important role in classical phase space. So if you are interested in like robotics, and in fact, you'll see in robotics courses that people teach in universities, Lie groups are essentially something they deal with because they help them understand how the dynamical systems can fit together. The unitary group is another Lie group that plays a very important role in quantum mechanics and our talk here. Heisenberg group is another one that captures the algebra of non-commutative operators like the position operator and momentum operator that's used in quantum mechanics. And they're also used in relativity. I won't get into this. The Lorentz group is essentially a group of isometries of Minkowski space, if you've heard of Minkowski space. These are examples. We won't be dealing with these groups. Okay, so we'll get to the groups that we care about. The two groups that we care about are the symmetric group, or the permutation group, and the unitary group. Okay? So we want to understand these two groups a little bit better. And in fact, we want to understand how they interact with each other, how their actions actually interact with each other on a set of vector spaces, okay, or a set of quantum states. If you have a set of quantum states that are put together, both of these groups act on them. Okay, yeah. So this is the next gear, I guess. So if you have questions on group structure or anything like that, just let me know before we get into symmetric group and its representation theory. I won't get into a lot of details of representation theory here, but we'll only understand just a little bit so that we can, first of all, connect it to, there's a connection to optics, but also how the algorithm works in this case. Okay, so the symmetric group is the group of permutations of n elements. Okay, by the way, pictures are coming soon, so be patient. So there are n factorial permutations of n elements, right? And every element can be written as, in the symmetric group, only transpositions are enough. So transpositions are simply exchanging two elements. So if you have, 1, 2, 3, 4, 5, you can exchange 1 and 2, or 2 and 3, or even 1 and 5, whatever. In fact, adjacent transpositions are enough. 1 and 2, 2 and 3, 3 and 4, 4 and 5. These are enough to generate any permutation. And you can easily just work it out a little bit, and you'll see that you can just, break it down into adjacent permutations. Got a question?
So, kind of go back to relation of the previous slide, this slide. So, you mentioned that the Lie algebras are differential. They're effectively a space, a vector space, in a real.
Real vector spaces.
Yeah. How does the permutation group fit into that? I don't understand.
Yeah, they don't fit in that structure, but they fit in as representations. And when I say fit in, it's not like you can fit one inside the other. It's just that their actions have a nice property. Yeah. So when I say fit, I'll make it precise in a minute. But it's not differential structure. That's not where it fits. In a sense, Lie algebras, especially the special unitary group, has the symmetric group in its root system. You'll see such coincidences all the time. So it doesn't really mean that symmetric group is embedded in there, but its root system has the special unitary group's root systems. The Weyl group of the root system is a symmetric group, it turns out. But you know, we won't be dealing with all those things. Yeah.
So I'm a little confused because when you first introduced groups, you said all we can do is multiply group elements and
Yeah.
other group elements. But now you're introducing operations on group elements like permutations.
Right. That's a very good question. What is multiplication in this context, right? So that's a good point, because multiplication, when I say multiplication, I just meant it very abstractly. And in fact, this is a very good place to see how multiplication has to be thought of as just an operation. It's not actually multiplying numbers. So if you have a permutation, let's say swap 1 and 2. That's the permutation in the symmetric group. Swap 2 and 3. So how do you multiply these two?
Those are different elements in the group. Each string is an element in a group, and now you're doing something to an element in a group as opposed to one element in a group working on another element.
Yeah, that's a good point. So the elements in the group here are the operations. They're not the permutation itself. They're not the end result of the permutation. So if you first arrange 1, 2, and 3, let's say is 1, 2, and 3, but now you swapped 1 and 2, so you have 2, 1, and 3. The element in the group is not 2, 1, and 3, but rather the swap, the operation. There are n factorial. You can swap all kinds of things, right? Not just swap, you can permute them in all kinds of ways. But yeah, so the operations are group elements. So what is multiplication now, right? Multiplication is just composition. Do them one after the other. So multiplying 1, 2, the swap of 1, 2 with 2, 3, right, is just do 1, 2 first and then 2, 3 after that, which is not the same as doing 2, 3 first and 1, 2 after that, right? So it's not abelian. So the operations are essentially, the group elements are the operations. Yeah. So you can, the transposition is denoted as bracket AB, is swap A and B. We'll use a notation that's kind of similar to this when you come to Young diagrams, but we'll get there in a minute. Okay, so here's where I'm just going to jump into representation theory. Now you'll have to excuse me for that. I'm sorry, but there's no other way to do this systematically in a 1-hour talk, except to say that associated with any group, any finite group, let's say, is a set of representations. Okay, I'll explain what a representation is, but why a finite group just has a set of representations associated with it is just a fact of nature, right? And it's a very important fact because that helps us use groups in a deep and meaningful way. Okay, now what is a representation? So as we just discussed, a group element is an operation. Oops, sorry. Is an operation. This operation can be represented as a matrix. So you can think of a certain vector space as 1, 2, 3, 2, 1, 3, and all possible permutations, right? You have n factorial such things. So in this case, it's just 6 of them. So it's a 6-dimensional vector space on which the operation of swapping 1 and 2 can be written as a matrix. How can you write it as a matrix? Well, you can just take 1, 2, 3. That's the first vector. 2, 1, 3. You can write it as 1, 3, 2. Then you have 3, 1, 2. And then you have 2, 3, 1. So 2 is over. You have 3, 2, 1. 3 is over, 1 is over. Okay, that's 6 of them, right? So this is a vector space. Okay. The operation of swapping 1 and 2 will take this vector, right, to this. So you have 0, 1, 1, 0, and this back to this, right? And then this vector here will go to 1, 3 to 3, 1, 2. So that's good. You have 0, 1, 1, 0. Okay, and these two to each other. So you have 0, 1, 1, 0. Okay, so you can write it like this. So this is a representation of the operation of swapping two numbers. And in this way, you can actually represent any permutation as a matrix. Sorry? In this case, but not all the time. In general, it'll be, for an arbitrary permutation, it'll be something else. So this matrix representation is essentially what people call a representation or a linear representation, because it's a matrix. You can, multiply it with a vector and stuff. And this lives on a vector space, right? So that's the dimension of that representation. It turns out that for every finite group, if you take any representation like this, you can sometimes break it up into a smaller representation, okay, by taking a smaller subset of the space on which you'll have some way of mapping these elements onto it. And by, so one other property of this, right, just as, so we'll call this R. R is the representation. This is R of the swap 1, 2. Okay, we're representing swaps as you know, bracket 1, 2, right? You can also write R of the swap 2, 3, and then you have R of swap 3, 1, and R of 1, 2, 3, all kinds of things. Okay, you write representations, they look like matrices. It turns out that if you multiply 1, 2 with 2, 3, this turns out to be R of 1, 2 times 2, 3. So as a group element, you can multiply 1, 2, and 2, 3 because they're abstract groups. But as representations too, the matrices, when multiplied, give you the matrix that represents the product. Okay, that's why it's a representation, because it respects multiplication in the representation and also in the group, right? You can multiply it in the group and then take the representation, or take the representation and multiply them and look at what the you know, end result is. And they happen to be the same. That's why the representation. That's why it's called representation. So this property gives you, you know, representation of certain dimension. It turns out that you can sometimes break the matrix down into a smaller matrix, right, where you have some R prime of 1, 2, which is a smaller matrix than this R, and R prime of 2, 3, which is the same as R prime of 1, 2, 2, 3. And not just for 1, 2, and 2, 3, but any two elements of the group have this property with R prime. In this case, we say that this is a sub-representation of the full representation. That's, you know, a natural. In fact, a simple sub-representation is one where, let's call it R double prime. R double prime of G is 1, the number 1, right? R double prime is this new representation. It's called a trivial representation. It takes every group element to the number 1. Well, it obviously satisfies this property. You multiply 1 a bunch of times, you'll get 1, and every group element, when multiplied, gives you that representation. This is called a trivial representation. And you can construct, so here's a one-dimensional representation. So here we saw a representation on a larger space. Here's a one-dimensional representation, right? So you have representations of different dimensions. It turns out that this cannot be broken any further simply because it's the smallest possible dimension. But it turns out that for many groups, there are higher dimensional representations that cannot be broken up any further, meaning that the only sub-representations they have are itself, right? And in fact, not even the trivial one. There's no other sub-representation, right? Those representations are called irreducible, and for obvious reasons, you can't reduce it anymore. So this representation can be reduced. I haven't gone through that reduction, but you can, you know, play with it. This representation is irreducible. Like this, you have higher dimensional representations that cannot be broken up any further. And here's the fact of nature that I was talking about before. Any finite group has a set of irreducible representations associated with it. Here, when talking about irreducible representations, I took a particular representation and talked about breaking it down and things like that. But you don't have to derive irreducible representations by picking a representation and breaking it down, right? You can actually derive it from the group. And the group has associated with it a set of irreducible representations. That set are all the irreducible representations, meaning if you pick any representation of the group on any dimension, you could pick it on 1,000, 10,000, whatever, such that they have this property, you will see that you can break that down into some set of these irreducible representations. There's a set of irreducible representations associated with the group which will comprise of any representation. Okay? So you can break it down, and you'll see those appear in them.
So as you said, the group multiplication itself, that's an abstract thing.
Yeah.
And in the case of the permutation group, you told us what exactly that is.
Yeah.
But you were saying that no matter what that is, once you have the group defined, all those four properties are satisfied, you can define a representation. The representation itself can be always thought of as matrix multiplication.
Exactly.
Okay. And what is the relationship between the size of the cardinality of the group and the size of the matrix?
That's a good point. So there is no obvious relationship. You can create representations on many different dimensions. The size of the group, there's a relationship between the size of the group and the dimensions of the irreducible representations. So it turns out there's a formula which tells you that if you sum the squares of the dimensions of the irreducible representations, this is the size of the group. And the number of these irreducible representations, how many will there be, that turns out to be equal to the number of conjugacy classes of the group. We won't need all those things. So there are many connections between representations, irreducible representations, and the group properties. But here, I just want to introduce or explain to you intuitively what an irreducible representation is and how it doesn't have to come from a representation which you try to reduce. While it doesn't come from there, it turns out that any representation comprises of irreducible representations. If you break this up, it'll just be a set of irreducible representations. And those irreducible representations have to lie in that set that I said the group is associated with it. Yeah. I mean, I don't think so. The word irreducible is used in many ways in various fields, right? So here, irreducible is exactly what it suggests, that a representation cannot be broken up into sub-representations. I don't know if the Markov chain take values in Lie algebras or something. Yeah, you could do random walks on groups, and in that case, the Markov chains may be associated. I don't know. It's possible. In general, when one says Markov chain is irreducible, that word doesn't necessarily mean this. Yeah, that's a good question. Okay, so irreducible representations, you have an idea what they are. Yeah.
So within the irreducible representation, it seems like multiplication within that group stays within
that set of matrices. Yeah.
It's a subgroup. Does it form a subgroup that's isolated?
So yeah, let's actually make sure we understand sub-representations versus subgroups. So when I say this has a sub-representation R prime, this is not of a subgroup. It's a submatrix of this. But for every group element, there will be a matrix that is smaller than this that you can associate with that group element. So subgroup will be a subset of the group elements, whereas here it's a sub-representation. But there will be a matrix associated with every group element that is of the same dimension, which is smaller than this. That'll be a sub-representation in this. And they have to satisfy this property that when you multiply the group elements and then take the sub-representation, it should be the same as taking the sub-representation and then multiplying those matrices. And yeah, so this representation can be broken up into sub-representation, these sub-representations into more sub-representations, and at some point it'll stop and you'll get these irreducible representations. And every representation, this procedure can be done. And essentially that's what quantum algorithms or even like classical algorithms, that's what people call the Fourier transform. The Fourier transform is essentially taking a big representation that's of interest and breaking it up into sub-representations until we cannot break it up anymore. And these irreducible representations are essentially the blocks in a diagonal form. And this block diagonalization is extremely useful in many applications. Why is it extremely useful? Well, you can think of as, first of all, if you're convinced that diagonalization of a matrix that's important, diagonalization, as in giving its eigenvalues and eigenvectors, helps understand the physics or the system better, then this is essentially doing something like that, but partially, right? It's block diagonalizing things. So that's why it's very important. In fact, Schur's factoring algorithm uses the Fourier transform and breaks up the cyclic group into its irreducible representations. For a cyclic group, which is an abelian group, all the irreducible representations have dimension 1. So there's no D associated with them except 1. But for non-abelian groups, there's at least one irreducible representations of higher dimension, like in the symmetric group. So the irreducible representations of a symmetric group are pretty complicated. In fact, constructing them was not easy at all. And there are essentially 3 different ways of constructing them. We won't be looking at them. But Schur-Weyl duality, Schur and Weyl looked at it. Schur-Weyl duality is one such way of constructing these irreducible representations. Okay? And they can be labeled. I mean, there's a convenient way of labeling them. And the reason for labeling them this way is actually that there's a lot of combinatorics that can be used, and that makes it simpler. They are labeled by something called a Young diagram. So here we are just labeling irreducible representations. So for any group, the set of irreducible representations is labeled G with a hat on top, okay, where G is the group, and this is some set, okay. For this, I mean, so we can, maybe it's R, we'll just put IIRR 1, and then there's irreducible 2, and so on. And there's a certain set, right? And this could have dimension, D1, this could have dimension D2. There'll obviously be one of them which is dimension 1, which is a trivial representation, and there could be more than one that has one dimension. And this is a set of irreducible representations, and any representation will contain some combination of things from here. Okay? And for the symmetric group, it turns out that instead of just calling them R1, R2, R3, we can label them by these things called Young diagrams. Okay? They look like this. Okay, so this is the description in words, but let me just show you a picture. So this is a Young diagram. Kind of, you can make people think you're doing something pretty fancy by putting numbers in them and stuff. So Young diagram is essentially a set of boxes that so this is for a symmetric group of certain size. Like, so here it's of size 3. And the number of boxes should be equal to 3. When I say size 3, I mean, how many letters there are, right? That's n that we were talking about before. The number of boxes here has to be equal to that. And they have to be arranged in such a way that the boxes on top have to be longer, and the boxes on the bottom have to be at least that length. I'm sorry, at most that length. As in, the second row cannot have more boxes than the first row. It can be 2. Here it's 1, but it can be 2, but not 3. Okay? So they should always look like, fatter or longer on top, and then they start getting thinner and thinner. Okay? They could be just a big box like this, that's fine, but the first row can't be this much, and the second row can't be longer. Okay? So Young diagram has this property. A Young tableau is essentially a Young diagram with numbers in them. So you have like 1, 3, 2, or 1, 2, 3. I'll be introducing much more stuff. So here's a joke about algebra seminars, okay, which this is somewhat related to, right? The first about like 40 minutes or so is spent on just definitions. And you can tell if it's an algebra seminar if you walk in like very late and someone's still explaining, oh, this is definition number, 123 or something. So here's some definitions. Okay, so a Young tableau is a Young diagram with numbers in the boxes, but we're interested in not just any way of numbering it in such a way that it's something called a standard Young diagram. Okay, a standard Young diagram is one where the numbers have to be increasing in any row or any column. In other words, 1 can only appear in this, and 2 and 3 can actually appear anywhere else. But you can't have 2 or 3 in this box, right? And you can play around with it to see that has to be the case. What's that? Oh, a partition. Yeah, that's right. A partition is essentially, so if you have n, a partition of n is essentially a way to break up n into pieces such that the sum of these is equal to n. So in other words, 2, 1 is a partition of 3, right? Because the sum is equal to 3. 1, 1, 1 is also a partition of 3. 1, 2 is also a partition, but we don't want to write partitions where the number of parts, or we want to write partitions in such a way that the number of parts have to be decreasing. So 1, 2 is not a valid partition in the way we want to write it. So 2, 1 and 1, 1, 1, things like that. Okay, so this is a standard Young diagram. Okay, Now, we'll skip this because this is not we won't be using this. Okay. There are some interesting formulae. So as I said, each irreducible representation has a certain dimension associated with it. And it turns out that because we are representing an irreducible representation with this Young diagram, there's a way to compute the dimension of this irreducible representation by looking at the boxes and calculating something called Hooke values. This is some combinatorics that's useful, but you know, let's not look at all that stuff. Okay, so that was the symmetric group. Now we look at the unitary group. Okay, this is much more complicated. I won't get into all the details because it has, you know, things called roots and root systems and stuff like that. But I still want to say that even though it's a continuous group which has in principle, like, you know, infinitely many elements, it still has the same structure. It has a set of irreducible representations. Any representation of this group as well can be broken up into pieces of irreducible representations. And again, as you know, to just remind you again, that is exactly what we're after. We want to break up a particular representation of the unitary group or the symmetric group into irreducible representations. Okay? So yeah, so the weight vectors lie in a certain vector space called root space, and you know, you can there's a lot of algebra that you can use in here. In fact, this is something that's that took a long time to figure out. So, you know, there's something called classification of Lie algebras, or simple Lie algebras, that Cartan and Killing did in the 19th century, and this was like one of the major achievements of 19th century mathematics. And that classification helps, you know, physicists now use those simple Lie groups to understand how particles interact with each other. Yeah, I should probably move ahead. But there's one thing I should say, that when I say simple Lie groups, maybe it's a bit of a misnomer, actually. They're not simple by any means. In fact, simple groups are far from simple. They were first called simple probably because people didn't understand them well. In any group, there's something called a normal subgroup. And normal is probably a good word for it because it helps you understand the big group. You know, looking at the subgroup and understanding it better and how it interacts with the rest of the group elements helps you understand the group itself. Okay. And you can think of a normal subgroup as something like a subrepresentation, not quite. But if you look at the normal subgroup now, you can maybe look at the normal subgroup inside that, and so on, and look at all the normal subgroups and take them, you know, aside, until you get a group that has no normal subgroups. That group was called simple, okay, because it had no normal subgroups. And it turns out that simple groups are building blocks of larger groups, just like, you know, irreducible representations are building blocks of these bigger representations. Simple groups are building blocks of larger groups and help you understand the bigger groups much better by looking at how simple or how normal subgroups interact with each other until you get to the simple group, right? So understanding all the simple groups there are and how they interact with each other in different groups, you know, helps you understand groups in general. So classifying all the simple groups of Lie type, or this continuous type, was the big challenge in 19th century mathematics, right? And Cartan and Killing essentially did it by understanding these root spaces of simple groups and classified all the simple groups. And it turns out that there are, like, you know, a set of, like, I don't remember exactly how many, but there are, you know, 4 continuous ones, or 4 or 5 continuous ones, and there are a few exceptional ones. And it turns out that most of them are important in physics now. And in a similar way to continuous groups, in the 20th century, people have classified finite simple groups, as in, like, you know, finite groups that we were looking at before, like the symmetric group and other things. All the simple groups that are finite. And in them, there's something called a monster group. And I won't talk about it, but Google it, and you'll see very fascinating things about monster group. Monster group is called monster because of its size. Okay. Right, subgroup adapted bases. So this is the last thing, pretty much the last thing I'll be talking about. And this is very important because, actually, let me show you a picture. Maybe that'll be easier. Yeah, we won't talk about Bernoulli diagrams, but where's the picture? Here. So this is what I was talking about in terms of representation. So here's the big representations that's kind of given to you from the problem. Okay, the problem kind of gives you this representation. When I say gives you, I mean it kind of pops up in the problem in a natural way. Okay, and understanding this representation is useful because it tells you maybe a lot of things about, if it's a physics problem, it tells you a lot of things about the dynamics, or if it's something in chemistry, maybe it tells you the properties. Like I said in crystallography, where the spectra, where the lines appeared, was important when you understand. You can figure it out when you understand these irreducible representations. So when I say this representation consists of irreducible representations, I mean you can change the basis here. So here the basis is something that we just kind of pick naturally, but you can do some unitary transformations and combine the rows and columns in some way, such that for every group element, right? If you do that same unitary transformation for every group element, you can break it up in a way that it's block diagonal, as in like everything gray over here is zeros. They're all zeros, and all the non-zero elements are only inside these colored boxes. Okay? And this is not for one matrix. It's the same unitary transformation, but all the matrices that represent every group element have this block diagonal structure. Okay? Only if the group is abelian will this be completely diagonal. Okay? And that's called a Fourier basis. That basis transformation is called a Fourier basis. Okay? I'm sorry, the basis transformation is called a Fourier transform. The diagonal basis is called a Fourier basis. For non-abelian groups, you can't get like a complete diagonal matrix for every group element, but you get a block diagonal one. And that's pretty good because it tells you a lot about the system. Okay? So that's essentially what people mean by Fourier transforms, or in this case, the Schur transform. Okay? So this is for some other group, but this is what we want to do. Oh, yeah, that's right. What are subgroup adapted bases? It's easy to explain in this picture. Subgroup adapted bases are where you don't just want the block diagonalization, as in you want that, of course, but you want more. You don't want an arbitrary basis inside this. Okay? You want a specific basis. Okay? And that basis has to represent subgroup structure. Now, this is related to your question where we were talking about subrepresentations, but what about subgroups, right? In this representation, if I just pick 1, 2, and 2, 3, and 1, 2, 3, or something like that, which forms some subgroup of the symmetric group, what we want is a did they form a, well, okay, we can figure out a subgroup, but the point is, subgroups have subrepresentations as well, meaning that every element of the subgroup forms a set of matrices here. And if you want to break up its representation into irreducible representations, you get irreducible representations of the subgroup, which is another group, right? So you'd get its irreducible representations. Now, it has its own Fourier transform and stuff like that. The point of subgroup adapted bases is so that you want to find a basis change inside each block such that when you go down to the subgroup, you don't have to do another transformation. It's already in its block diagonal form. And then you go down to another subgroup, it's already in its block diagonal form. So subgroup adapted bases are, you need to specify a subgroup tower. Okay? So subgroup adapted bases are with respect to that tower. And as you go from the top of the group down the group, you don't have to change bases anymore. Okay? That's the point of subgroup adapted bases. And why are subgroup adapted bases important? Simply because you tend to look at things as in an asymptotic way. Okay? So you have like n particles right now, but then, or n vector spaces or something like that, and then you want to know what happens if it's 2n or something like that. And subgroup adapted bases help you understand how this progression takes place. So natural subgroup towers for the symmetric group are simply, you could just, for 1, 2, 3, for example, or actually let's just take 1, 2, 3, 4, 5. The symmetric group on 5 elements, right? It has 5 factorial permutations. These are group elements. You could look at a subgroup that fixes 1, meaning look at all the permutations that don't touch 1 and just permute the remaining 4. That's only 4 factorial. That's a subgroup of this group, right? Then you can look at the ones that don't touch 1 and 2 and only permute the remaining 3. And then fix 1, 2, and 3 and only permute 4 and 5. And then fix 1, 2, 3, 4, 4 and permute only 5, which is nothing, and fix all of them. So this tower is called a subgroup tower, right? That's a natural subgroup tower. And in the unitary group, you have a similar subgroup tower, which is given by, oh, sorry, it's before this. Well, yeah. So it's, so a unitary group is on a dimension D. You could reduce the dimension little by little. You get, different unitary groups, and you go from all the way from 1 to D. You get unitary groups one inside the other, and these are all, subgroups of the full unitary group. So it turns out that this is a natural subgroup tower for the unitary group. So subgroup adapted bases are with respect to such a tower for any group. Okay. So we want subgroup adapted bases because block diagonalization is useful, but then we want the information inside the block as well. It's not just that we want block diagonalization, right? Just like how after we diagonalize a matrix, we want the eigenvalues, that is information in the one by one block, right? So in the same way, we want information inside this bigger block. So we want to kind of come up with a nice basis for that. And subgroup adapted bases are such bases. Okay. So subgroup adapted bases have been considered by mathematicians for a long time, and Gelfand and Zetlin came up with a set of bases for the unitary group, and Young and Yamanouchi came up with bases for the symmetric group. Okay, and Young, actually, Alfred Young is someone who's spent a lot of time understanding the symmetric group very well. In fact, his name figures extremely prominently in all of the symmetric group representation theory. These are all called Young diagrams. So, and it turns out that the basis of the unitary group also can be labeled by, irreducible representations of the unitary group can also be labeled by these Young diagrams. And the subgroup adapted bases essentially let you go from these Young diagrams by pulling out boxes, by removing them as you go down the tower. Okay. So, how do we get to subgroup adapted bases? Well, so the rule to go down this tower is first, just one step, is pick any column. For each column, either remove a box or not. Okay, that's the rule. So from this column, you can remove a box or not. From this column, you can remove a box or not. But if you remove a box from any column, let's say this one that I have a pointer on, you can't leave it in a way that's not a valid Young diagram. So if you remove this box, you have to remove this box as well. Okay, so that it's never the case that there's a hole inside this Young diagram. It should be still a valid Young diagram. And if you recall what a valid Young diagram is, it's essentially one that has more boxes, at least as many boxes on the top rows as the bottom one, right? So if you do that, the possibilities for this is not do anything for any column, remove this one, then you get this, remove this one, in which case you have to remove both of these and you get this, or remove, what do we remove here? Remove this one and these two. Yeah, each column you have a choice of removing a box, right? So you can remove this one and these two, so you get this. So these are all possibilities. And from each of these, you can go down one more down the tower, a subgroup tower, by removing another box. And you can actually label the boxes in the way that you remove them, right? So you can label the boxes in such a way that you keep track of how you remove the boxes. That'll give you something like this. It's called a semi-standard Young diagram because you put, so what did you do over here? Let's go backwards here. These two have 1 because, sorry? Here? Here? Yeah, here there's no extra box. We didn't remove anything. Yeah, you can do that too. Yeah. Yeah, it's a little bit, but I mean, it turns out from group theory that these are the rules to follow. But yeah, so I mean, you can do this later if you like. But these two have 1s because these are the last to be removed, both of them at the same time, right? There's no other way. So these two have 1s, and that's what we see. Oops, I'm sorry. That's what we see over here. These two have 1s, and the 2's are over here and here because that's what we removed to get here, right? And then there's 3's in the remaining 3 because that's what we removed from here, right? So you can, so essentially the subgroup tower or a basis for this can be represented by these semi-standard Young diagrams, okay? So in a similar way, you can get semi-standard Young diagrams in the symmetric group, okay? So you can get a way to label these things in the symmetric group, and you can also see that these 1's and 2's and 3's have a nice structure that they call horizontal strips, meaning if you take away everything else except boxes labeled a certain number, they form something called horizontal strip, meaning that no 2 boxes are in the same column. There could be gaps, but that's fine. No 2 boxes are in the same column. And horizontal strips play an important role in the algorithm. And the other thing to notice is that you can stitch together the entire thing by just stitching together horizontal strips. Horizontal strips are simply, it's saying you peel away the 1's, peel away the 2's, peel away the 3's, and each one looks a little bit like this. There's never like stacked on top of each other. It could be spread out. Yeah, so that's basically it. So, you start from some point and you start building the representation from the bottom, and as you keep moving up, you'll get to the irreducible representations of the full group. And these subgroup adapted bases come about because we kind of keep track of how this representation fits inside the bigger one, right? And I'm out of time, right? Okay, let me finish with this last part. So, what is Schur-Weyl duality? I mean, we've talked about symmetric groups, we've talked about representation, subgroup adaptive bases, and all kinds of things. Schur-Weyl duality essentially says, I mean, this is your question of how they fit together, right? It's saying if you take V tensor n, V is some vector space, okay, and you have n copies of this, and you can think of them as quantum states living in that Hilbert space, right? And they're all the same, so you have V tensor n. So if you permute them in any way, it's the same thing, right? If you have the same vector inside it. So the symmetric group acts on this space and preserves it, or it has an action on this space, right? You can write matrices inside the space where symmetric group of permuting 1 and 2 tensor copies, what that means, right? The unitary group also has an action, meaning on each copy of V, you can do a certain U, okay? And the same U on the next one, and the same U on the next one, and all of them have the same U, okay? This is a unitary group representation. It's something. Now, you can see that these two commute with each other, meaning that you can do one of them first and the other one second, and still it's okay. Meaning, let's do U tensor U tensor U and all the copies first, and then permute the copies in some way. Okay, because it's the same U, it doesn't matter. You can permute them. Or, before you apply U, you can permute the vector spaces, and then apply U tensor U tensor U. It's fine. So the two of them commute. Okay. What that really means is that V tensor n can be broken up into irreducible representations of the symmetric group, which is V lambda, okay? Tensor, some representation of W lambda, okay? Which is a unitary group representation. Schur-Weyl duality says that this W lambda is not just a representation of the unitary group. It's an irreducible representation, meaning that if you break up this V tensor n into irreducible representations of the symmetric group, what you end up with on this space, which is called the multiplicity space, is an irreducible representation of the unitary group. You can view it from the unitary group side as well. If you think of this as just a unitary group representation and break it up into irreducible representations of the unitary group, which are W lambdas, you'd get some number of copies of each W lambda, which is inside this space. But it turns out that this is not just a representation of the symmetric group, it's an irreducible representation. What this is saying is that, at the group level, is this. If you look at all possible permutations of the symmetric group, right, on this, and say, well, on V tensor n, I can permute the tensor copies, and any operator you apply A tensor A, I can permute it. Okay, that commutes with the symmetric group action. But then you want to know what are all possible operators on V tensor n that commute with that symmetric group action of permutation. Maybe there's A tensor, B tensor, C, of some complicated, ABC, that still commutes with the symmetric group action. It turns out that if you look at all possible operators, or in other words, the maximal commuting algebra that commutes with the symmetric group algebra, it turns out to be the unitary group algebra. As in, no other operator commutes with the symmetric group action that's not inside the unitary group. That's why these two are special, because on V tensor n, they're maximally commuting algebras. That is, you take one algebra and look at its action, and look at all the possible operators on V tensor n that commute with this algebra, you'll find the other algebra. Okay? And that's why they're paired. And that's why these two statements are equivalent, that these two are irreducible representations and that they're maximally commuting. These two are the same statement. Okay? One is a representation theoretic statement here, and the other one is a group theoretic statement. Okay? So that's Schur-Weyl duality. And as you can see, we can approach it from the symmetric group side or the unitary group side. Okay? And this is essentially comes down to my algorithm, which I have here. Let me skip this and give you the circuit. Okay, it looks very simple, right? But to prove that this is what it does this is not that easy. But yeah, essentially the circuit. I mean, it's in terms of primitives, so I mean it's not this simple, obviously, right? This is QFT is not a primitive gate. It's not a gate in the gate set. It's a subroutine, right? And R of G is not exactly a gate in the gate set. But the point is that you can start looking at the unitary group representations and then break down each of them, the whole thing into block diagonal form, or you can look at the symmetric group and do that in the block diagonal form. You can take either one of them, and Schur-Weyl duality assures you that you will get the block diagonalization with respect to the other group as well. Okay, and that's the important part. So the previous approach to this by Bacon, Chuang, and Harrow, they've looked at it from the unitary group representations. And because it's U tensor U, they have to do it iteratively. You take U tensor U, you combine them, block diagonalize that, then take the next U and combine them, block diagonalize it, and do this n times. Symmetric group permutes the whole thing at once, and what I have is essentially an algorithm that uses symmetric group representation theory and not the unitary group, and that block diagonalizes this. And it uses some of the previous work on symmetric group quantum Fourier transforms and things like that. In a sense, it's, the circuit at least can be represented in a cleaner way. And in terms of the dimension of the unitary group, it's exponentially better than the published version, although Aram has a way to do it using theirs, which he didn't publish. Where is it? Here. So the previous algorithm is polynomial in d, n, and log 1 over epsilon. Epsilon here is the precision, n is the number of copies, and d is the dimension of each copy, right? But this algorithm here is log d, n, and log 1 over epsilon. Polynomial in n can't be improved because even the basic operations require poly n steps. Log d is exponentially better than the previous one. It probably can't be improved as well. So yeah, it gets you to the Gelfand-Zetlin basis and the Young-Yamanouchi basis, which is subgroup adapted in both. All right, thank you for listening.